Um, Let me welcome you to this fourth lecture of our class on reinforcement learning. We are going to complete the four-lecture overview of the course with two special control problems and methodologies. Adaptive control, and after we take a break, model predictive control. So adaptive control deals with problems where the model parameters are changing over time. We're going to give some examples of such situations. They are very common. And then we have to do something to counteract the changing parameters because what we have been using in the way of control may not be effective anymore. Model predictive control is another major methodology in control system design. Its architecture is very similar to the AlphaZero architecture, and we are going to discuss this methodology in the context of applications in control theory. Then we're going to take some time to take stock of what we have done so far. The four lectures that we have gone through, including today's, are going to be a platform from which we can go in several different directions. We cannot follow all of these directions, but we're going to follow some of these directions, particularly rollout, some approximation using neural network material. There are other directions that we will not cover, and we're going to list them here, but you're going to be free to follow them on your own. So let's go into adaptive control. It's a very old methodology, more than 50 years old. And it involves problems where the parameters of the problem, be it the system equation parameters or the cost parameters or the constraints, may be changing over time, and then the control has to adapt. As an example, let's look at a cruise control type system. Where we want to keep the velocity of a car close to some target level, which may be adjusted by the driver. Now, the state of this simplified version of the problem is just the car's velocity, which we call xk. Xk is the velocity of the car at time k, and it evolves over time under the influence of the propelling force, which is this u here. And it changes like so, and A and B are coefficients. A models, for example, the friction on the road, wind drag that slows down the car, and B depends on a number of parameters. How far you press the pedal is this UK. However, how much force, effective force, is applied on the system may depend on the road, may depend on the weight of the car, like the number of passengers in there. So all of this may be changing over time, in addition to the set target level of the velocity. A reasonable cost function here is a quadratic one. X bar here is the target velocity. We want to keep the state near this target velocity, and there's a quadratic penalty for deviating from that velocity. And there's also a quadratic cost on the control, where R is a positive number, fixed number. On the other hand, this is not the usual linear quadratic problem that we have seen before, because A, B, and also X bar may be changing over time. They may be measured, perhaps with some error, certainly with some cost. It's hard to measure this A and B, but you can estimate them with some error, perhaps. Overall, this problem is far more difficult as an optimization problem relative to the problem where A, B, and X bar are fixed. So that's the type of situation that adaptive control deals with. And there are several different approaches. One possibility is to just ignore the changes of the parameters. Just don't bother to estimate them. Don't bother to just pretend that they don't change, and then design a controller that is robust in the sense that it works in some sense, for example, stable. It works for a broad range of parameters, and then let it go at that. It's the simplest possibility, but as you can imagine, the least effective. A second possibility is to try to actively estimate the parameters as they are changing, and then use the estimates to modify the controller. For example, once we detect that the parameters have changed, we may do online replanning by optimization. In other words, modify the controller to make it optimal for the new set of estimates. So the controller may be assumed to be optimal for the current set. This is called indirect adaptive control, and some methodology that has a long history and a long string and has been successful in practice, and it's quite popular. One of the principal methods of adaptive control. Now, here's another possibility. Instead of going through reoptimization, which can be costly and may not be able to be done exactly online, instead do it approximately, do online replanning by rollout. Just use rollout with some base policy and estimate the cost values that you need for rollout, estimate them or compute them by using the current parameter estimate. In other words, as the system is changing, the rollout algorithm will also change, but it's not as it's not as time consuming as a full-blown reoptimization. So this is simpler. The third possibility does not separate between estimation and control, estimation of parameters and control. The more principled approach, it formulates the adaptive control problem as a POMDP, partially observed Markovian decision problem, with the unknown parameters, which are hidden, being viewed as part of the state. And then after we formulate the problem as a POMDP, which is very, very hard to solve exactly, we try to do it approximately in some of the reinforcement learning methods that we know. So these are the three different methods, and we're going to discuss them one by one. Are there any questions here? Okay, let's talk about robust control. Here we have a system with control input and some output here that we can observe, and the system may be changing over time. However, the controller is fixed, and the output of the system is fed into the controller, which applies control, and we just ignore the changes in the system. We act as if it's all the same. Make no attempt to estimate them, and hope that this fixed controller will give you acceptable performance throughout the range of the system changes. So this is a very simple approach. However, does it work? Well, sometimes it works, sometimes it doesn't. In general, it is a risky approach. However, there is an important example, an important special case, which has proved successful over time. And this is the PID controller, a very old control system, goes back 100 years. And PID stands for proportional integral derivative. And it involves three parameters, which are tuned experimentally or some kind of heuristic method, sometimes manual method. Okay, the output here, there's a single output, and this output is the deviation of from some desired output, some fixed point that you would like to keep this output at, and you measure the error between the true output and the desired output. And the three parameters weigh these errors. The instantaneous error at the current time, accumulated errors, That's the integral part, and changes in the error over time, this is the derivative part. Just 3 parameters, and you tune them in, and you don't even know what's in this box at all. Now, the limitation of this is that it applies primarily to the single input, a scalar control, a scalar output. There have been efforts to extend the PID control to more general type of situations, but that has met with varying degrees of success. On the other hand, there's a very seductive aspect of the PID controller. You don't need a mathematical model. You just plug this box into your system, and then you tune this parameter somehow, and you're in business. So it's important, before we put down too much this approach of robust control, it's important to remember that there's a very successful representative of this approach. Let's go to the second approach, which is known as indirect adaptive control. Here, the system has parameters that are changing, and we get data from the system. We observe the system to the extent that we can, and we estimate this parameter. So if the system, let's say, moves to some different regime of operation, we try to identify that and try to estimate the new context within which we're operating. Now, every so often, the parameter estimates of the model are fed into the controller, which adapts itself, hence the name adaptive control. So the controller is recomputed so that it's optimal for the current set of parameters. You can view this as an alternation of system identification phases, where the system is identified through this parameter estimation box, and then a controller reoptimization part that takes place in here. And we alternate between system identification, controller reoptimization, and this can be done simultaneously. Now, one of the problems of this is that it can be time consuming. You may have to apply control every 2 seconds, but the reoptimization may take a few minutes. So that's not very good. That may be a problem. There are also some interesting interesting theoretical issues regarding the possibility of identifying the parameters simultaneously as we control the system. It may be that the control process may hide some of the parameters of the system from identification, and this can cause a problem. Your class notes discusses this a little bit with an example. People have been able to deal with that. Parameter identification or system identification is a very active area of control system design, and people have been able to modify schemes to be able to deal with this problem. But I just don't want you to think that this parameter estimation process is simple. It is not. It requires a lot of thought and interesting algorithmic design. So let me give you an example now, and then you can ask your questions about robust and indirect adaptive control. So in this example, it's a simple one-dimensional linear quadratic problem, like the ones that we have been dealing with, particularly in the previous lecture. It's one-dimensional, xk plus 1 equals xk plus b uk, okay? And the cost is quadratic. And we want to control the system basically around 0. And we want to apply control that's not too large, as dictated here by this quadratic penalty. However, contrary to our previous treatment of linear quadratic problems, let's assume that b is unknown or it changes, okay? And let's compare a robust controller with an exactly reoptimized controller, as in indirect adaptive control. Okay, suppose we pick a robust controller, which is a nominal controller that's optimal for b equals to 2. Here on the horizontal, I have the coefficient b, okay? And for b equals to 2, I find the optimal controller in the way that we have discussed in previous lectures, using the Riccati equation, the linear controller, and we use this for a range of values of b. The reoptimized controller estimates b, and we assume that the estimation is exact. In other words, at any one time, it calculates b, it has b available, be it here, be it here, be it there, and applies the optimal policy for that b. So now here on the vertical is the cost coefficient, the quadratic cost coefficient. In either case, with a linear robust controller or with a reoptimized controller, the resulting cost is quadratic, and the coefficient of the quadratic cost is k. So this corresponds to higher costs, and the optimum cost for b equals to 2 is right over here. And as b decreases, well, I need b smaller, so I need larger views, basically, and that adds to the cost over here, and so the cost increases as b becomes smaller. Now, this is reoptimized, and what you would get with a robust control is certainly bigger, but you see that there's quite a bit of discrepancy. This is the loss, the penalty that you pay for using a robust controller and not having to estimate b as it changes. So you can see that there is some penalty to be paid. Is this example clear? Do you have some questions? Okay, so let's now discuss reoptimization, which is approximate by rollout, and we'll return to this example after we do that. So here parameters are changing, and we replan by using rollout instead of reoptimization. So there's a computational and estimation cloud here, which looks at the changing system, estimates parameters, perhaps estimates various and other system parameters or constraint parameters, and passes these parameters onto the controller. Now, the controller at time xk does not use the optimal policy for the current set of parameters, but instead uses its parameters to modify a rollout policy, a one-step look-ahead policy in this particular case. We use one-step look-ahead, a terminal cost function approximation, and roll out with some base policy, presumably a robust policy, which is good for a broad set of parameters. However, this is not a robust controller because it involves rollout, which is a form of reoptimization, approximate reoptimization. Now, this is cheaper, computationally speaking, than controller reoptimization. Instead of reoptimizing every so often, we just use rollout, and which is much less expensive computation. We continue to use the same robust base policy, but there's also a possibility of recalculating the base policy in the background and pass it on to the controller once every so often. So it's not quite as good, perhaps, as full reoptimization, but it is a significant step in that direction. And now I'm going to argue that this is almost as good as doing exact reoptimization. The reason is that rollout is very effective, and if the parameters are close to their nominal values, they don't change too fast, then the rollout tracks very effectively the reoptimized controller. So here's the same example I had in the 2 slides ago. a linear system, quadratic cost, a changing coefficient b, which is being estimated and it's passed on to the controller. Now, the robust policy ignores this estimate, just doesn't use it. The indirect adaptive control, exact reoptimization, uses it and recalculates the optimal policy. And what you see is this curve here. Now, using rollout in place of full reoptimization is almost as good. Only at the edges here, it starts changing a little bit. And there is no comparison with that's far more effective than the robust base policy. Basically, from here to here, there's a Newton step. And that Newton step is so effective, it's almost optimal in this particular case. So are there any questions here?
I have a question from a student.
Okay.
This is minor, but to be clear, the starred points are the reoptimized policy, right? The yellow stars.
The yellow stars are the
Okay.
reoptimized rollout. Is the rollout.
Okay.
And the black line is the black curve is the exactly reoptimized.
All right. Yeah, it's a little hard to make out here.
Yeah, they're so close. It's hard to make out. Yeah, you're right. Yeah. Yeah. All of them coincide when the base policy is optimal when b is equal to 2. Remember, the base policy is optimal for b is equal to 2. And here we're varying the parameter of the system. And as we vary, of course, the reoptimized is going to give you the lowest cost. The approximately reoptimized with rollout is almost as good in this parameter. In fact, on this side, they're almost the same, very hard to distinguish in them. On this side, they start to diverge right around here. But of course, there's a big difference between the performance and performance of the base policy. This difference is due to the Newton step, the one step look ahead. And that's what it is.
I have a question. So
Yes.
just to clarify if I understood correctly, so between the robust base policy and the reoptimized rollout policy, it's basically the base policy remains the same, but the only difference is that one step look ahead, and then the difference between the rollout and the exactly reoptimized is that the exactly reoptimized doesn't do one step look ahead, but instead it recomputes the controls for the new B at every step. Is that correct?
Yes, you said it exactly right. The base policy stays the same, and the rollout simply uses one step look ahead with this base policy for the remainder. Whereas the reoptimized doesn't care at all about the base policy. It simply finds the exact optimum for that particular parameter, which is given by the estimator. So
does this increase the complexity if there are multiple control options at any step in such a scenario?
Well, you have to take into account that this is an academic example. Excuse me. Here, everything can be done analytically, right? In linear quadratic problems, the beauty of them is that you can calculate everything analytically. You don't have to resort to simulation or approximations or whatever. In a different problem, then these computations may become substantial, right? The rollout may be substantial computation, but the exact reoptimization may be even worse, far worse.
Yeah, true. Okay, thank you.
Okay. So let's go to another approach, which is more principled. Here, there is no artificial separation between estimation and control. We first estimate, then we control, then we re-estimate, then we readjust the control, and so on. Here, everything is done simultaneously together in an optimization framework involving a POM-DP, which is, of course, very hard to solve exactly, as we know, as all POM-DPs are. So we have a system that is deterministic, but it involves some unknown parameter. And for simplicity, we assume the parameter can take a finite set of values. Let's say M, 100 different values, or 1,000 different values, or whatever. It could take a continuum of values, but for it's easier to understand if the number of values that the parameter can take is known. We do not know the parameter. We have a probability distribution a priori, for example, the uniform on this set of parameters. And then as the system evolves, we update the probability distribution of these parameters, and then we use them for control. So here's the system. It involves a state xk, a control uk, and a parameter theta. And we assume that we observe the state exactly. There are more complicated formulations, but here we're going to assume perfect state observation. And we use this as measurements to update the probability distribution of the parameter theta. In other words, we estimate the belief state. We calculate the belief state, the conditional probability that theta has a particular value from this set, conditioned on all the information that we have collected so far. And the information we have collected so far at time k are the states that we have observed, the current state and all the previous states, and also all the controls that we have applied in the past. In POM-DP parlance, it's called the information vector. It's all the information that we have collected, and we assume that we have an estimator that online calculates this conditional distribution. This may be non-trivial, okay? But it can be done to some extent, exactly or approximately in given cases. And now we have a POM-DP involving an augmented state. The state of the system really is xk, which is perfectly observed, and theta, which is hidden. Theta does not change, but we just don't know its value. So this is the augmented state, and we formulate this as a POM-DP. And for this POM-DP, we can write a Bellman equation. And this Bellman equation has this form, okay? It could be a Bellman equation as a function of the augmented state, but here an alternative, which is possible, is to have the optimal cost of time k be a function of the current information. That's certainly a sufficient statistic. It's possible to argue in terms of dynamic programming with this being a state. And this is the Bellman equation. Okay, to justify this Bellman equation takes a lot of tedious computation. So what I'm going to do is explain it in intuitive terms. Remember, all Bellman equations involve optimization, minimization over the control of the sum of two things: the expected cost of the current stage and the expected cost to go. Now, expected in what sense? What's the uncertainty here? The uncertainty is this belief state, this belief distribution. So this part here, the summation, the weighted sum with the belief probabilities of the cost, gives you the expected cost of the current stage, okay? Theta I is not known, so we take its expected value with respect to the current belief probabilities. And this is the optimal cost to go from the next state, which is the next information vector, ik plus the new state, xk plus 1, plus the new control, uk. So this equation has all the markings of a Bellman equation. Minimization over u of the expected cost of the current state plus the expected cost to go, assuming that we act optimally from this point onward. So, of course, solving this equation is totally impossible, except in the most trivial of the trivial examples. And approximations are called for. And what are the approximation methods that we know? Well, approximation in value space, where we approximate this thing, which is very hard to compute, with something, some approximate thing that makes sense. And then we minimize over u here with j tilde replacing j star. So it is convenient here to use approximations that depend just on the new state instead of something that depends on the information, all the past information and the control. So everything, all the past gets encoded in this j tilde through xk, uk, and theta, the current parameter value. That's why we have I here. In other words, this approximation depends on theta. We use a different approximation for each value of theta, each of the possible values. And then we minimize here over u, and we obtain a one-step look-ahead policy. And if we can calculate either in closed form or more likely by simulation, this expression here, this is a feasible computation. Now, what can we take as j tilde I here? One possibility is to take it to be the cost function of the optimal policy corresponding to theta I. In other words, for each of the possible values of the unknown parameter, we act as if we know that value. In other words, this is optimal cost under a clairvoyant assumption that we know what theta I is. And there are m of those, one for each theta, and we use them in here and weigh them with the corresponding probability. So it's some sort of expected value of cost to go, assuming the clairvoyant assumption that we know what the theta I is. Another possibility is to use as j tilde the cost function of a known policy, again under the clairvoyant assumption that we know theta I. So there's a different one for each different value of theta I, and we use some known policy, some heuristic, to calculate this expression for each value of theta I. And then we weigh them with the corresponding probabilities in here. And this is rollout. This is the analog of rollout for POM DT. So we're going to look at this scheme in a future lecture, and we're going to combine this type of scheme for other problems that have the characteristics of have unknown parameters. This type of scheme, you may ask, why do we need to go to this scheme and not the previous one? Well, this scheme is better suited for situations where the control decisions may imply the choice of observations on this system. And it may be that we may want to choose control with the view of enhancing the observation process in the future, like use better kind of observations, things like that. Okay, we will see examples of this type of situation in a future lecture. And there is a section, there are two sections actually in chapter 2 of your notes dealing with this sort of scheme involving unknown parameters. What I'd like to do is give you an example that's close to my recent experience. Are there any questions, by the way, in this slide before we go to the example? Okay. I guess most of you are familiar with this word puzzle. Many people are, many people play, millions of people play this puzzle every day because it appears in the New York Times and it has become very popular. It came around about a year ago, and it immediately got the word on fire. Everybody, so many people are playing this puzzle every day. And this involves unknown parameters and decisions. It may surprise you that this is an adaptive control problem. However, let me say a few things about the puzzle. You probably know how it works, but I'll describe it briefly. We have a collection of mystery words. In the New York Times version, it's about 2,500, 2,500 mystery words or so. And one of those is chosen every day. And you want to try to guess that mystery word with as few guesses as possible. And there are guesses that can be drawn from a list of about 12,000 or so. So the New York Times picks a mystery word for the current day, and you pick guess words. So here the mystery word is inert. The first guess is audio. And then if you choose this word, then as a response, you obtain information about the commonality of certain letters between the mystery word and the current guess word. Here there are 5 letters, and one letter I is common between the two, but not in the exact same position, in a different position. And these are painted yellow. Okay. Then this information is important, right? It makes you more. It affects your. It should affect your following guesses. So let's say in the second guess we pick this word here. Now this word has quite a few letters in common with this one. It has E and R are common and in exact same position. T is common, but in a different position between mystery word and current guess. Similarly with N. Now, at this point, you've learned all the letters. You have 4 letters from here and 1 letter from here. So you will know the exact 5 letters that the mystery word contains. And then, okay, you can guess the word. It is inert. So it took here 3 guesses to obtain the mystery word. So that's how the problem works. And what's the connection with adaptive control? Well, theta is the unknown, the unknown parameter is the unknown mystery word. It takes values from a set of 2,500 words, which you know. In the a priori distribution for the New York Times case is the uniform distribution. Then the way to formulate this problem is to view as state the list of possible mystery words. In other words, given all the guesses so far, up to guess K, we can construct the list, a subset of all the possible mystery words that are consistent with the information that we have gotten so far. And then U is actually a mistake here. U is the guess word, not the list of possible guess words. U is chosen from the list of possible guess words. So an unknown mystery word is chosen in the beginning, this theta, and then you apply U, you apply decisions, and you narrow down XK, the list of possible mystery words, until it consists of just one word. So you have all the elements of an optimal control or adaptive control formulation. dynamics, the way system dynamics, in particular, the way in which the list of mystery words evolves over time. You have decisions, which are the choices of guess words, and you have a cost function. The cost function, you pay 1 unit for every guess that you make. So you can view all this. You can write equations. You can set in the formulation that I gave in the previous slide, and theta here is part of the augmented state, which is and it's partially observed. Xk is fully observed. Theta is partially observed through the results of the guesses that you make here, and you update the corresponding beliefs. The very nice thing about this problem is that the belief distribution is actually uniform over the list of possible mystery words. A more difficult version of this problem is when the initial probability distribution of the guess of the mystery words is not uniform and becomes considerably more difficult. Now, it is possible to solve this problem exactly by dynamic programming, and people have done it. For each different initial mystery word, they have calculated by dynamic programming the optimal policy. That takes, according to one report, takes days of computation using a lot of parallel computers. So it's a highly non-trivial computation. It's a gigantic dynamic programming computation that's aided by the special structure of this problem. Now, in an alternative approach, which we have applied with 2 of ASTU students, is to use rollout in the way I described it in the previous slide, and use as base policy one of several base heuristics that have been used. There have been a lot of heuristics used for this puzzle. For example, one that chooses a guess that provides maximum information, quote unquote, or apply a guess word that gives you that shrinks as much as possible the size of the current mystery list. There are several base heuristics, and we have used rollout in the way I described in the previous slide with several of these base heuristics. And my collaborators are 2 of the students that took this course last year, Siddhant Bambri and Amrita Bhattacharjee, and they did their term paper on this. It was their idea. They did this term paper on the world puzzle, and they were quite successful initially. And then working further on the problem, we got some very good results. And now we have an arXiv paper that's online that you can consult about the details and the results. I'm going to have Siddhant and Amrita discuss the algorithm at a later lecture. But for the moment, I'm going to give you just the result. The optimal performance with the optimal choice of the optimal performance for the problem is 3.5084 average number of guesses, average over all the possible choices of the mystery list. Now this average over the 12,500 choices. And this is the optimal number. It's calculated by this gigantic dynamic programming computation that I mentioned earlier. Now, rollout solves this problem in seconds and gives you a result that's within less than 0.5% from the optimal policy. It's essentially optimal for all intents and purposes, but it is much faster. And not only that, if you complicate this problem and make the mystery word and the mystery list larger, or make the number of letters larger, let's say all the letters are 6 or 7 letters rather than 5, or you introduce a non-uniform initial probability distribution over a mystery word, the problem becomes intractable. No matter how many parallel computers you use or how many weeks you try, you can't solve this problem exactly. However, the rollout policy still works in seconds, in the order of seconds. So our approach scales with problem size, whereas the optimal approach will work only for very special problems and with a lot more computation. So Siddhant and Amrita will talk about this implementation at a later lecture, a few lectures from now. And but we're going to leave it at that at this point. Are there any questions? Okay, that's all I have to say about adaptive control. Let's take a 15-minute break. We'll reconvene to discuss model predictive control, and you can bring up your questions at that time. So we'll meet in 15 minutes. So are there any questions about this first part of the lecture before we go into model predictive control? Okay. Well, model predictive control is a prominent control system design methodology. It's a hardcore control methodology. It is of particular interest in connection with reinforcement learning because it shares the architecture of AlphaZero. So architecture is very close to AlphaZero with a few differences that we're going to discuss. But before we get into that, let's talk a little bit about control theory and what are the core problems in control theory. There are two classical problems. One is control around a reference point, and the other is control along a trajectory, a pre-planned trajectory. Okay, in the first problem is you have some kind of a reference point, and you would like to control the system around that point. And usually the reference point is chosen to be 0. By translation, you can always bring the reference point to 0. And here's an example. You probably have played around with this example, at least the real version, not the software version. Here we try to keep a pole that has a mass attached at the top. We try to keep it upright. So the pole tends to move, but we want to keep it upright by providing some counter force. And we want this angle here to be 0 or close to 0. And we want the pole to be at rest, not to move at the upright position, which means that its velocity, the angular velocity, is also 0. Theta dot here is the first derivative with respect to time of theta. This is really a continuous time system in reality, but it is, but we discretize it in order to treat it computationally. We discretize time to treat computation. The way we want to keep this pole upright is by applying forces on this cart here that holds the pole. If it veers to the left, we want the force to go in the opposite direction, and so on to the right. And we just apply these movements here to keep it still. And that's representative of a regulation problem. In other cases, for example, chemical process controls problems involve having temperatures, pressures, and compositions be around set points, and they use control system models of this type. It's a very, very common, perhaps the original control problem. Next type of problem is path planning, where we want to keep the state of the system close to a planned trajectory. Like have this car follow a particular trajectory from point A to point B. Now, an important part of this particular example are the constraints. The car has to stay on the road, but also has to avoid these obstacles here. Otherwise, we'll crash. There are also some constraints on the velocity of the car. If it goes through a bend and it goes very fast, then it will get off the road and crash. Similarly, there are constraints on how much acceleration you can apply or deceleration, braking you can apply. These are, again, physical constraints of the car. And these are hard constraints. In other words, you can't violate them. If you fall on the obstacle, you're going to crash, and that's the end. So it's critical to obey these constraints. Similar with chemical process control. If your pressure goes above a certain point, then the whole reactor is going to explode, and then you're in trouble. So it is very important to address constraints. And in fact, that has been the motivating factor behind MPC, model predictive control. It addresses state constraints much better than linear quadratic formulations or other methods. There's some other aspects about this problem that's interesting and complicating. The fact that obstacles may be moving, like other cars on the road. You can crash onto them, and you can predict when they are going to appear and at what point. So it's important in some of these problems to be able to do online replanning, path replanning. And this brings us a connection with adaptive control. In adaptive control, you also have to do replanning, right? When the system changes, the problem changes, you have to replan. And this is also part of the model predictive control concept. So let's try to address now the problem mathematically. We're going to use approximation in value space. And the original form of model predictive control operates as follows. It assumes a system that's stationary in this particular case. And it's nonlinear, possibly. And it has a cost function that is positive everywhere except at the origin. Now, this formulation addresses the regulation type of control problem, where you want to keep the state of the system near the origin. So we impose a positive cost for being outside the origin and also for applying non-zero control. And the cost is exactly zero for x equals to 0 and u is equal to 0. So in other words, we assume that the system, and also the system can stay at the origin at zero cost without paying any cost. So once you bring it to the origin, then in this formulation, you have the control stops. In reality, there's always some uncertainty. You can't bring the system at the origin exactly, or if you can, it may go off the origin, in which case in reality there's control applied continuously. But for a mathematical approach to the problem, we assume that once you bring it to zero, then it stays there. So what is MPC? Instead of optimizing this cost function over an infinite horizon, you impose a finite horizon, and we impose the requirement that the state n steps ahead from the current state is brought at zero. So that's the problem that you solve in MPC given the current state xk. You find a control sequence over L stages, and and we require that this control sequence brings the state to 0 exactly after L steps ahead. And we also require that the cost here, we impose the requirement of costs here over this L stage is minimized. Now, after we minimize the cost over the L stages, then we apply the first control of the minimizing sequence and discard all the other controls. Now you can see that this is related to approximation value space. We have one step look ahead for the first stage, plus a cost approximation for that models the minimization over the remaining L-1 steps. So you can view this as rollout, with a base heuristic being the policy that minimizes the drive from xk plus 1 to 0 in L-1 steps. So this is the base policy, and this is the one-step look ahead. You can also view it as a general type, sort of, what makes it a little different here is that there's a hard constraint on the state. So it's a little different than the approximation value space scheme that we had discussed, but it's a perfectly legitimate rollout scheme. Another thing to note here is that this is very well suited for online replanning. If the system changes here, or some of the constraints change, then you can introduce this into this minimization. You can introduce this change in the minimization, and which amounts to online replanning. Now, we mentioned that in MPC, state constraints are very important. This formulation allows control constraints, but I haven't shown you anywhere any state constraints. And I have left them for later. We're going to discuss state constraints, which are very important, in a few slides. But for the moment, we're going to focus on simpler versions of the problem because state constraints require a special treatment. Are there any questions about this slide? This is not the form of MPC that's very common in practice. It's the original form, but it suggests other forms which are common in practice. And I'm going to give you in the next slide. A very common variation of model predictive control is when we introduce a terminal cost function approximation instead of the requirement that the state is driven to 0 in L steps. So we use a non-negative terminal cost for the end of the L step horizon, and we solve the problem that you see here. This is one step look ahead, L step look ahead, minimization with this terminal cost function approximation. So this is our standard type of multi-step look ahead approximation in value space. It's of the type that we have considered, but we can also complement it with truncated rollout in between here with some base policy. This has some advantages. It also brings it more closely to the AlphaZero and PD-Gammon architecture that we have discussed in the past. All the elements are here. Multi-step look ahead, truncated rollout in the middle, and terminal cost function approximation. It's the same thing. The main difference between this architecture and the PD-Gammon architecture is, first of all, this is deterministic, where the PD-Gammon is stochastic, but there are stochastic versions of this as well. But more importantly, the state space is continuous and the control space is continuous. Whereas in games like PD-Gammon and chess, the state space and the control space is discrete, finite. It corresponds to the different moves and different positions. As I said, this is a common formulation, and the MATLAB implementation of model predictive control is based on this here. And we may introduce also state constraints in this minimization, whereby the successive states from state xk to the last state xk plus L have to be in some constraint set. And then this is one of the most general forms of MPC. Note that we make no assumptions about the nature of the state space, of the control space. It can be continuous or discrete, or a mixture of the two. In control theory, at least part of the state space is continuous usually. The state constraints we have not dealt so far, but we are going to deal with shortly. An important question about which control theorists worry about very much. When is the MPC policy stable? Now, for this to be true, G must be in the region of stability, which brings the question, how do we know what the region of stability is? We have some information where it lies, but not precise information. And there are conditions that G must satisfy in order that B can satisfy and be guaranteed to be in the region of stability. But I'm not going to go into the mathematics of this. You can look at the class notes. Let me note here also that truncated rollout with a stable policy helps very much in bringing G into the region of stability. And that's an important advantage of rollout within this context. Again, this is an extension of the type of figures that we saw in the previous lecture involving the graphical interpretations of rollout, policy duration, and approximation value space in connection with Newton's method. There's a Newton method hidden in all this, as it was in previous treatments of this type of architecture. Are there any questions? Okay, so now let's address state constraints. We mentioned earlier that they are very important. And the state constraint that we're going to consider is of the form that xk has to belong in some subset. So everything has to happen within a subset that doesn't violate the obstacle constraints or other constraints. And it's important that you start in there and also stay in there. Otherwise, you have difficulty. To introduce state constraints into the MPC formulation, we have to modify the MPC problem. And this problem takes the following form. Assuming that the current state xk belongs to the constraint set, the MPC problem is to minimize the cost of L stages plus the terminal cost subject to the control constraints, but also the additional state constraints. So part of the formulation here is that x0 must start in x, and also note that the control obtained by this minimization, the first control in the sequence obtained from this minimization, is guaranteed by the definition of the problem to generate a state xk plus 1. So this formulation assumes that you start with an xk, and there is a control that brings you into, that keeps you into the constraint set. In other words, it assumes that this problem is feasible. But the difficulty here is that there is no guarantee that this problem has a feasible solution. It may be that there are starting points within this constraint set, and no matter which control you apply, you escape from there. It's too late. You can't bring it in. You can't keep it in. So the question is, how do we make sure that this doesn't happen? In particular, how do we guarantee that this problem is feasible for all, at all times and with all states, initial states? Let's give an example to explain what happens here. Suppose that you have this scalar system. xk plus 1 equals 2xk plus uk. And notice that this system is unstable. It tends to go up, right? The state doubles with every step. And let's assume that there's a control constraint, that u must take values between -1 and 1. Now, if the state is very large, then because of this term here, no matter how hard you try with the control, you push in the opposite direction, you can't bring it back within reasonable values. So let's consider this situation. Let's consider state constraints of the form that xk has to be within this set. In other words, its value has to be between beta and minus beta, where beta is a scalar. Okay. So let's suppose that beta is greater than 1. I have plotted here as a function of k the constraint set. So at time 0, the constraint set is this, between beta and minus beta, or like that, or between 1 and -1. Okay, and that constraint remains for k equals 1, k equals 2, and so on. So the constraint set, this constraint set defines a cube of values within which you have to stay between beta and minus beta. Now I claim that if beta is greater than 1, if the constraint set here involves a beta greater than 1, so the starting state can be outside this white cube, then the state constraint cannot be satisfied for all initial conditions. And the problem is that if you are far from the origin, either in this red region over here or in this red region over here, the state increases too fast for the control to be able to bring it down within the white region. In particular, suppose we take x0 to be equal to beta, okay, satisfying this constraint. Then 2 times x0 is greater than 2. And x1 is going to be 2x0 plus u0, but u0 can only be -1 here. Its absolute value has to be less than 1. So the next state will be bigger than the previous state. So what happens is you start with x0 equals to beta, and you get x1 that's even bigger. And the same rationale can be used to prove that the entire sequence of generated states will be increasing, and also will tend to infinity. So in other words, what I'm saying is that if you start here in the red region initially, then the state trajectory is going to explode no matter what control you use. So this kind of state constraint cannot be used in MPC. It will violate, it will eventually violate any kind of limit that you may have on the state. On the other hand, suppose that you use an initial state that's within this white region, okay? Then you can stay within that region by applying control that's between 1 and -1. 2 sub xk is going to take you somewhere to at most 2 beta, and then a control -1 is going to bring you back into the white region. So what's happening here is that the state constraint can be satisfied provided that it has this form. For x0 in the set here, you can satisfy the state constraint, and the MPC problem is feasible. Now, sets like this one, where if you start anywhere in them, at the next state, the state will be still within them, regardless of for some suitable value of control, they are called invariant. You start within the white cube, you can stay within the white cube by suitable choice of control. So let's discuss this invariant sets in the next slide. And Here is the requirement for invariance. This is the same example that I gave earlier. A set X is said to be invariant if, starting from any point within that set, there exists some control which is feasible, such that the next state is still within that set. So you start in here, you can always stay in here and satisfy this constraint. And that makes MPC possible and the MPC calculation feasible. Now the problem here is that how do we calculate an invariant subset of a given constraint set? Now, this can be done, but it's typically an offline calculation. So that's the problem with these invariant sets. You have to have them from the beginning, and you cannot recalculate them online. It turns out, certainly you can see it in this example, but in general, there exists a largest possible invariant set. For a given control constraint set and for a given system, you can find invariant sets, but there is one that contains all others. This is the largest possible invariant set. And you can see in this example, this is the largest invariant set. Any other invariant set has to be contained in here, because if it contains points that are outside the red region, then you have this problem of instability that I described earlier. It's possible to compute this largest invariant set by using something that looks like value iteration. You start with some set that is not invariant, and then you go one step back and you get something smaller and smaller and smaller and so on, until you get into the largest possible invariant set within the set that you started. It's a substantial computation, but there are also easier other possibilities. And there's a lot of literature about all this. This literature started, let me say, with my PhD thesis, long time ago, more than 50 years ago. My PhD thesis was the first one to address this issue of invariance, and actually in a more general context involving also W's and certain quantities. And unfortunately, for a very long time, nobody paid any attention to my thesis, which was very disappointing to me. But about 15 years later, the idea of keeping the state of the system within confined regions became important in contexts like robust control, and it's really important in model predictive control. And this was recognized quite a few years later when MPC became popular, starting in the late 80s and 90s. Okay, it's nice to see that sometimes, even though your work is not recognized, eventually somehow it comes to the surface as the field progresses. So are there any questions about all this? You can find a lot more in the literature about the invariant sets, about how they can be used in MPC and other contexts. And there's also your class notes, chapter 1, have references in a little bit more detail than what I have given you here. Questions? Okay, we're not going to talk much about MPC in future lectures, which brings up the question, what have we done so far, and where we are going, and also what we will not cover. As I said, the first 4 lectures are intended to give you an overview, a foundation for looking more deeply at other reinforcement learning topics. and also incidentally to get you started on your term paper. So you can start from your class notes and expand and try to find something that's of interest to you. So what have we covered so far in our 4 lectures and also in the class notes, chapter 1 of the class notes? We looked at exact dynamic programming in all its major forms: deterministic, stochastic, discrete state space and continuous state space, finite horizon and infinite horizon. All of this, of course, was in summary, but I hope I gave you the main ideas, at least at an intuitive level. Then we identified the major problem with exact dynamic programming, namely calculating the optimal cost to go. We introduced approximations, and particularly approximation in value space with one-step look ahead and multi-step look ahead. This is the workhorse in reinforcement learning. Everything, not everything, but most of reinforcement learning is built along various components of approximation in value space. It's also the foundation for some of the major success stories, including AlphaZero and PD Gamma. And we argue that approximation in value space consists of 2 components which can be designed more or less independently: offline training and online play. And there's a synergy between them through Newton's method. We focused on the fundamental methods of policy iteration, and it's 1 iteration version, which is rollout. Policy iteration involves policy approximations and cost approximations in between iterations. So it's primarily an offline method. On the other hand, rollout is less ambitious, but it can be applied online and is simpler. Both of these have connections with Newton's method. This is 1 step of Newton's method. This is multiple steps, or an infinite number of steps of Newton's method. Then we discussed some of the major models that can be used within dynamic programming. Discrete optimization is one. We're going to come back to this. FOAM-DP, imperfect state information, multi-agent problems, and in this lecture, adaptive control and model predictive control. Finally, a recurring theme within our presentation was the fact that we use function approximation, cost functions or policies, most commonly cost functions. And we have alluded to that in various places, but we did not go into detail on how you do these approximations using, for example, neural networks and other architectures. So this is the content of chapter 1, and from this we can build into other directions. So the first chapter is a foundational platform, and we're going to go in some depth on the rollout and its variations. For example, applied to discrete deterministic optimization problems, multi-agent problems, and some of these adaptive control problems that I gave earlier in this lecture. All of this is in chapter 2 of your class notes. Then we are going to discuss also in chapter 2, sequential decision-making in some special contexts involving changes in parameters, sequential estimation, Bayesian optimization, and simultaneous system identification and control. And we're going to have this lecture on Wordle that I mentioned there. This is also in chapter 2. Chapter 3 on your notes deals with offline training for approximation in value and policy space using neural networks and other approximation architectures. We're going to spend at least 1 lecture on this topic, and this is all in chapter 3 of your notes. this is what we are going to do for the rest of the semester. These are the things that we are not going to do. Reinforcement learning is a vast field worked on by many different communities with different applications in mind in different cultures. So there's a lot more that what we are going to cover. I hope that this first chapter provides the platform, but you can go in these directions on your own. Stochastic algorithms, a very big part of reinforcement learning. They are used primarily in the context for policy evaluation, offline policy evaluation in the context of approximate policy duration. You'll see names such as temporal difference methods, TD lambda, and other methods, Q-learning. All of this is part of, all of these are stochastic algorithms that can be used with some success. I would say varying degrees of success in the context of policy evaluation. Aggregation is another topic. It can be used for cost function approximation, essentially by creating a smaller system out of a bigger system by lumping states together and solving the smaller system. And in this way, it can be used for cost function approximation and also approximation in value space. Now, reinforcement learning involves a lot of data, right? Data for self-learning, data, performance data for various policies. How do we collect this data in the process of offline training? And also, how do we do this for cost function approximations and also for policy approximations? It's a very big part of reinforcement learning within which we're not going to go. A lot of theoreticians, statisticians, worry about statistical estimates of various sampling methods, like confidence intervals, or methods involving simulation, trying to do simulation efficiently, use few samples for the same effect, for the same value. This is a mathematical subject that a lot of people work on. On the other hand, I gave you the argument that Newton's method is the big equalizer. In other words, worrying too much about efficiency in constructing cost approximations is not so important. Once you are within the region of convergence of Newton's method, then it doesn't matter how many samples you're going to use, additional samples you're going to use. It's all the same. So anyway, a lot of people worry about this, and it's a big theoretical subject of research. Finally, all of the methodologies that we focused on, such as POM-DP, model predictive control, adaptive control, and so on, have a lot of applications. Robotics, automated transportation, many different types of applications that you can find within the exploding literature. We're not going to go too much into this, except for some sample applications that are going to be in chapter 2 and 3. On the other hand, you're free to choose the topic of your term paper from within these topics here, even though we don't cover them in class, as long as they're couched on this foundational platform of our first 4 lectures in chapter 1. So are there any questions here about what we have covered and what we will cover or will not cover? Okay, well, this is going to be a shorter lecture than you expected. But I thought that we should stop here to have a clean separation between generalities and specific topics covered in depth. In the next lecture, we're going to go into rollout and its variations for deterministic problems and also for stochastic problems to the extent that we have time. About your homework. We gave an extension of 1 week for the homework. So there will be no homework, no new homework this week, but the new homework is going to be announced next week. And for these subjects here that we are going to cover, you may watch video lecture 5 from the last year's offering. So that's it for today. We'll see you next week.